Right, so very good mornings to Datuk Shida Ahmad, judges, participants, ladies and gentlemen. Welcome to Innovate Malaysia Designs Competitions 2021's online grand finale under Keysight tracks. I'm very pleased to be here as a session chair. I'm Dr. Chi, currently serve as associate professors from Lee Kong Chien's Faculties of Science and Engineering, University Tunku Abdul Rahman Sungai Long campus. Together with me, we have the coordinator, Mr. Hong Jing Hit, will assist the events. It is special assignments. We have vice presidents and general managers, order fulfillment Keysight's Malaysia site general manager, Datuk Shida Ahmad, in joining these auspicious events. Without further ado, I would like to invite Dr. Datuk Shida Ahmad to deliver an opening speech. Please join me in welcoming Datuk Shida Ahmad. Datuk Shida, the floor is yours.
Thank you very much, Dr. Chi, and a very good morning and hello, everyone. Really happy to be here to see our 5 team finalists on their last leg of the Innovate Malaysia Design Competition. And to all the 5 teams, congratulations on making it to the finals for the Keysight track. I know you have been working very hard over the last couple of months. And if I look at all your projects, I'm very impressed by the caliber of your work. And not only that, the relevancy of the projects to what's happening in the world today. Now, each of the teams have shown creativity, skill, passion, and perseverance in this journey of innovation. More so in spite of this current COVID movement control situation that we have. So this culture of innovation is so important and even more crucial now than ever. You know, the world's getting much more complicated, complex, and challenging. If you think about it, right, the challenges impacting our quality of life, our sustainability, and in fact, survivability of our life. Of course, we're right in the middle of a global health crisis in COVID. We have climate change, we have pollution, depletion of natural resources, and we need innovative solutions to tackle all these tough challenges. And at the same time, if you think about it, technology is also advancing and transforming the world at a very fast and exponential rate. The smartphones of today, for instance, are at least 100,000 times more powerful than the early commercial computers in the 1960s, you know. And do you know that the iPhone that you have right now in your pocket has enough computing power to conduct a space mission to land man on the moon? So if you think about it, we are truly in the midst of a digital revolution, and you know, the situation that the world is facing, like COVID, has further accelerated the pace of digitalization and also transformation. And all this is propelling us to a new innovation paradigm. We have to create faster, we have to keep pace with the accelerated rate of technology complexity. And the only way that's critical in making that happen is innovation. It's going to help us thrive and grow in this environment. So we need innovators who will continue to raise this bar of innovation. Now, Keysight Technology, as a technology leader, is very committed and very excited to help all of you, our young innovators, on this journey. We want to create many opportunities for you to learn, for you to create and innovate, like this Innovate Malaysia Design Competition. All these platforms are going to be important to build stronger knowledge for you, allow you to network and be more exposed to new technologies and real world challenges. So for all the innovators on the line, you are on the right track, you are on the right path, so continue innovating. I look forward to seeing you create breakthrough solutions that's going to help us thrive and improve the world. You have the power in your hands. So I wish all of you the very best. While only one of the teams will get to the real grand finale next week, I want all of you to feel very proud of your achievements. To me, every one of you are already a winner. So good luck and all the best for your future. Thank you very much. Over to you, Dr. Chi.
Thank you so much, Datuk Shida, for that kind speech. I'm sure your wisdoms will inspire them. And so I wish best luck to Keysight, as Keysight is a very good pioneers in leading the technologies and also to cultivate the youngsters and also the young generations in making a difference in Malaysia. So thanks for Keysight's effort. So let us have small sessions for photo takings to memorize these special moments. I would like to invite all the audience to turn on your cameras for photo sessions. And the photo will be taken from Keysight. So, yep. Let me stop sharing my screen. So yes, today events wouldn't be a success without the support from our honorable judges. So please join me in welcoming the judges teams from Keysight Technologies. They are Mr. Chai Hu Yuan, Ms. Jessie Lim, Ms. Julia Hong, Mr. Liu Chi Kang, Mr. Mayalagan Kanyan, and Mr. Wong Ming Wei. It is time for the participants to unleash your talents and present your ideas to the judge. So each team will be given 15 minutes for presentations, 5 minutes for Q&As, and 1 and 2 minutes for overall comment from Keysight. To ensure the smoothness for today's events, reminders will be given when it is time's up. At 14 minutes, the coordinators will inform there's only 1 minute left, and at 15 minutes, the coordinator will inform when it is time's up. So, a very big thanks to all of the teams. Let us welcome the first teams from University Tun Hussein Ons. UTHMs with the project's ID MYZ32 with the titles Developments of Monitorings and Notifications Applications in Wearable Device for Biosignal-Based Stress Detections, presented by Aminato Shaida binti Jumat Ali and Latifas binti Abdullah, which is supervised by Madam Zarina binti Tukirans and TS Dr. Shamsul bin Muhammad. So all the presenters are reminded to turn on your cameras during the presentations. So Aminatos, the floor is yours.
Thank you. So right now I will share my screens, my presentation screen. All can see my screen right now?
Yes.
Okay, thank you. I will start with my member will start the present.
Okay, you may start whenever you are ready.
Okay. Hello, and good morning. My name is Aminatul Saadia binti Jumali, and my group member is Latifah binti Abdullah. Our group is from MY0332 from Keysight Track. Our advisor is Madam Zarina binti Tukiran. We are from University Tun Hussein Malaysia from Faculty of Electrical and Electronic Engineering. Okay, problem statement. In this COVID-19 pandemic, students are not excluded from having stress. With the sudden change in the learning method from face-to-face learning to online learning, students face many distractions at home, which contribute in rising the stress level, and many parents are extremely concerned on this matter. Okay, problem statement. In this COVID-19 pandemic, students are not excluded from having stress. With the sudden change in the learning method from face-to-face learning to online learning, students face many distractions at home, which contribute in rising the stress level, and many parents are extremely concerned on this matter. For the current solution and our limitations, nowadays many wearable devices that measure heart rate for stress detection are sold worldwide. However, heart rate value can be increased by many factors other than stress, such as excitement or in pain. So, these devices might be inaccurate and triggering false alarm since it only depends on heart rate measurements. Plus, those devices are able to notify single user only, which is not helping for the concerned parents. Therefore, there is a need to detect stress from multiple physiological inputs to minimize the false detections and provide multiple notifications. So our solution and why it's better. Our project is able to detect the stress condition based on two clinically proven biomarkers of stress called heart rate and skin conductance. It is able to provide notifications to multiple users. This is our target segment and impact. Our device is not only for students, but it also suits everyone. Users will be able to take necessary action according to their stress condition before it becomes harmful to the health. For parents, it helps them to monitor the mental conditions of their children and able to lend a hand during their child's hard time. For the methodology, it consists of three parts. First is the fuzzy logic modeling for stress detections. The second part is the development of the prototype. And the last one is the graphical user interface GUI of Blink applications. For the methodology, it is we use fuzzy logic modeling for stress detections. It's the development of the prototype. It consists of Arduino Uno 20x4 LCD, ESP8266 Wi-Fi shield, SD58C power sensor, and LM324 Groove GSR sensor. This is the SD58C power sensor that used to measure the heart rate. It is a photoplethysmography or PPG biosignal to measure the heart rate. For at the front part, the light emitting diode LED and the ambient light sensor are coupled on the first surface. And at the back of the sensor, the circuit, this is the circuit that is responsible for the noise cancellations and the amplifications is connected to the second surface. Is the LM Groove GSR sensor. It is galvanic skin response. GSR is stand for galvanic skin response, or also known as electrodermal activity EDA biosignals to measure skin conductance. For this is the third part is the graphical user interface GUI of Blink applications. At the Blink applications, we have notification 1 that shows the conditions. We use gauge 1 and gauge 2. For the gauge 1 is to display the heart rate value, and for the gauge 2 is to use to display the skin conductance values. 4 LEDs are used to indicate the conditions of the body, and the notify 2 shows an appropriate message at the Blink applications. This is the results and discussions. It has accuracy testing of fuzzy logic system for stress detections. This is the output stress condition for PSNet inputs dataset of rest state. The output of conditions of fuzzy system match with every input combinations of the PSNet inputs dataset of the rest state. Therefore, the accuracy for the dataset is 100%. Right now, I will play our project demo. Can I ask, do you hear the music background of this slide?
Yes.
we can.
Yeah, we can.
Yes.
Thank you. Wait, The wearable device is connected to the power banks as the power supply. It consists of two types of sensor. It is pulse sensor and GSR sensor. The result of heart rate, skin conductance, and body conditions is displayed at the 20x4 LCD.
When heart rate is above 100 beats per minute and skin conductance is above 20 microsiemens, the condition is stressed, indicates as 4 red LEDs and display the advice, which is take a deep breath and relax in blink application. Then a push notification will be displayed as stress detector alert. You are stressed. Take a deep breath and relax. It's okay to take a break. When heart rate is above 100 beats per minute and skin conductance is below 20 microsiemens, the condition is slightly stressed, indicates as 4 yellow LEDs and display the advice, which is take a deep breath and relax in blink application. Then a push notification will be displayed. When heart rate is in between 90 to 100 beats per minute and skin conductance is above 17 microsiemens, the condition is tense, indicates as 4 yellow LEDs and displayed the advice, which is take a deep breath and relax in blink application. Then a push notification will be displayed. When heart rate is below 90 beats per minute and skin conductance is below 17 microsiemens, the condition is relaxed, indicates as 4 green LEDs and displayed the advice, which is you are in good condition in blink application.
This is the video demonstrations of the prototype for the wearable device. The pulse sensor was velcro strapped to the subject's finger, while the GSR sensor was strapped on with the provided straps. In these videos, for the first test, the subjects are in the rest phase. The participants were asked to relax while watching a variety show video at YouTube channel on the computer for 1 minute. The result of heart rate, skin conductance, and body conditions is displayed at the 20x4 LCD. Next, for the stress test, the subject were asked to do an online brain game. The operator in Brain Gamer is a problem-solving online brain game in which subjects are required to track an operator belonging to the equation given by doing mental calculation. During the game, each question time limit lasts for 5 seconds and the operation changes for each question. If the participant had completed the task after 1 minute, it ended automatically. The result of heart rate, skin conductance, and body conditions is displayed at the 20x4 LCD. And that's the end of our video demonstration. Thank you. And lastly is the conclusions of this project. Our stress detector device able to detect stress conditions by using two biosignals. It is heart rate and skin conductance. And it also able to notify multiple users so that the user and concerned individuals will be able to take necessary actions according to their stress condition before it becomes harmful to the health. Thank you.
All right, thanks for your nice presentations. So I'd like to invite Q&A from judges.
Yep. Hi, Aminato. This is Maya here. Yeah, so this is a very useful invention for current stressful environment. So interesting innovation. So just curious how you determine the threshold or limit for the heart rate and skin conductance for you to determine or you categorize as stress, tense. or slightly stressed, relaxed, like mentioned just
Actually, I will show it's not shirt. Wait, Okay, this is the implementations of fuzzy rules. So this is the table to detect between the stress and not stress, tense or slightly stress.
Yep. So, but how you come up with these numbers?
From our previous reference, we do lots of studies from the previous references. It says that if there are only for normal conditions, we have 60 to 140. The maximum is 140 BPM, and for the skin conductance is from 2 microsiemens to 41 microsiemens.
Okay. So this is basically from your literature study.
Yes.
Okay. Okay, thank you.
Thank you.
Yeah, Aminato, I have one question. Does skin conductance, the reference value of 20 microsiemens, right? Does it varies between genders and races?
For the for my readings, it doesn't say that if the females and the males, the maximum is 20 microsiemens. It's only said when humans are human skin conductance is between 2 until 20 microsiemens only.
All right, okay. Does the skin conductance change during exercise?
Yes, it changed.
Okay, so that means when you exercise, you are always under stress, right? Because your heart rate increase, your skin conductance also.
Because when we exercise, our skin conductance or BPM it will increase, right? So we only conduct the testings for when the person is doing the mathematical questions only. For the exercise part, we will not test.
Okay, all right, thanks.
Aminato, this is Julia here. So you
Yes.
just mentioned that there are conditions that make your device accurate. For example, you must be in a rest mode, not just exercise and you test it. What other conditions have to be met to make your device accurate?
I'm sorry. Can you
Okay.
explain?
You understand my question?
Yeah.
Yeah.
For the sorry, can you repeat that?
Okay. To ensure your device give correct results, there are conditions to be met. For example, don't test it after you exercise. You mentioned just now, right? What other conditions other than this? Yeah.
Like because the systems are sensitive when people are before means after exercise, so I'm not taking that one. And also I'm only taking when that person is on relax only.
Okay. All right. Maybe if you have opportunity to work further on this, you can actually quantify your prerequisite so that results are more accurate.
Yes.
Right. But great job. Thank you.
Yeah, thank you.
Hi, Aminato. This is Jessie here. I have one question for you.
Yes.
Just now you mentioned that your solution is able to share results with multiple users, but in your demo it wasn't shown. So how is it being done?
We use Blink applications for the notifications. Like Blink applications can be downloaded on the endpoint, right, from the Play Store or from iOS. So when we download the applications, it uses our emails. So multiple users can use same email and get the notification.
So one result will it be able to share with different people? Like you say, one of the use case is to monitor your kids' stress level. So if the
Yeah.
parents would like to know the condition, are they able to do the setting and receive the notification?
Yeah, they because the notifications we do the scopes is for to get the notifications for the parents. So when the parents get notifications of their children's, they know that the children's are in a stress state, like because right now students they are stressed but they are not telling their parents. So from the parents get notifications and can see the conditions of their children.
So it's through email notification, lah, right?
The email is push notifications from the phone. It's not it's email. Like we receive a notification from WhatsApp, it's like that.
Thanks.
Okay, thanks. So can we invite Josh to make the final comments about the overall projects for around 1 or 2 minutes?
Yeah, Minato, I think your project overall, it is, I would say, quite a practical things to apply, especially during this time. And everybody is stressed,
Yes.
students, even those are working from home for prolonged period of time, they will also be under certain stress, right? So overall, your project is quite innovative. I think you did all your necessary validation, right? It's also practical. In terms of complexity, well, maybe you can incorporate the other sensors apart from the GSR and also the heart rate sensors. But overall, great job to you and your team members, and hopefully this can be, I would say, commercialized, and all of us will be wearing this one day, right? Okay, thank you.
Okay, thank you.
Thanks for the comments from judges, and thanks Aminato for your presentations. Very nice presentations. So I would like to proceed for our second candidate from University Tunku Abdul Rahman Sungai Long campus with the titles Developments of an AI-driven wearables object recognition device for rehabilitation's purpose. The ID numbers with the MY071 presented by Mr. Lim Chu Chen and supervised by Dr. Ji. So, Mr. Lim, the floor is yours.
Hi, good morning. Morning, everyone. Can you hear me clearly?
Yes,
Yeah.
morning.
Okay. Hi. So let me start off with the presentation. So a very good morning to all the judges and the participants. My name is Lim Chu Chen, and today I'll be presenting on my submission for this year's IMDC 2021 competition. And my project is titled Object Recognition Smart Glove. So I will start off this presentation by showing you an overview video of my project and the problem that this project aims to solve. So some of you might have seen this video already, but please bear with me. This is for those who hasn't seen it yet, and I'll be covering more after the video. Okay, so let me share my screen. All right. Let me know if you cannot see or hear the sound.
Hi, my name is and this is my project titled Object Recognition Smart Glove, a glove that provides strength to those who need it. Let me start off this presentation by giving you a scenario. Meet Alex. Alex is an 87-year-old man diagnosed with dementia leading to Parkinson's disease. For those of you who don't know, Parkinson's disease is a terrible progressive brain disorder that affects the nerve cells in the brain responsible for body movements, and there is currently no cure, so only preventative and rehabilitative measures could be taken. People affected by this disease would usually have difficulty in body movement and body coordination, and that was what happened to Alex. He had an extensive loss of hand function with a limited range of motion and reduced strength in his hands. When Alex's family found out that he had this disease, his family immediately researched on what could be done to delay the onset of this disease. They found out through their doctors that Alex should immediately start with rehabilitation exercise training through physiotherapy. So that's what Alex did. He started daily sessions with his physiotherapist in hopes that he can form a muscle memory and gain strength for his hands. So traditionally, how a physiotherapist would gauge hand function assessments is through a mechanical or an electrical goniometer placed across the joint of interest to measure joint movements. These devices are highly intricate and requires extensive knowledge of joint movements to gauge the progress of the patient. Therefore, only specialists such as physiotherapists has the knowledge to gauge the performance of an individual in a quantitative manner. This is a problem for Alex, as this means that he has to meet with his physiotherapist at least a few times a week or he wouldn't be able to see his progress. Not only that, moving here and there causes a lot of strain on his already weak body. So this means that he has to rely on his friends and family to spend the extra time to care for his needs, such as transportation to and from the physiotherapy center. Alex was my grandfather. Unfortunately, he passed away a few years ago due to complications with this dreadful disease. However, he has inspired me to take on this project, which I believe would be a huge help for those in a similar situation. I have created a smart glove that can recognize objects using a supervised machine learning algorithm. This glove is able to track the degree of joint movements and it is able to predict the object that the user is holding with the current self-learning network. Also, with the data produced by this glove and its slight change in programming, this glove can also track the grip strength, joint mobility, and pinch strength of the user. A machine learning algorithm can then be applied to gauge the improvements of the user over time. So, why do I believe that this product will be better over the current market solutions? The first is, as I've mentioned above, this product ultimately does not require a specialist to gauge your performance. This means a reduction in visits to the physiotherapy center, as the rehabilitation training can be done at home with instant feedback from the glove. In any case, if a specialist advice is truly needed, the data from this glove can also be used by the physiotherapist to gauge the long-term performance of its users. Another benefit is the versatility of this product. The example that I've given above is just one of the many applications that this product can apply to. Another use case would be that this glove can be used in the virtual reality or augmented reality landscape. As this glove can provide accurate finger movement data to a computer, there will be no need for bulky and handheld controllers to control elements in the virtual world. The machine learning model of this project allows for a wide range of applications due to its self-learning nature. Finally, and arguably the most important aspect of this project, is the cost. As you may or may not know, consumer-grade equipment, especially for rehabilitation purposes, can usually cost very high due to the lack of competition and the monopoly around the industry. Case in point, the picture on the left is the current market solution for a smart rehabilitation glove. The one on the right is the cost of the professional package of this glove, which allows practitioners to create patient profiles. The working principle of the glove essentially is similar to the prototype that I've developed. With this current solution, it is no wonder that the average consumer would much rather spend the time to visit rehabilitation centers to use their equipment rather than spending the thousands of dollars to purchase one for personal use. However, my solution was completed with the budget of a full-time university student with no grants or sponsorship from external parties. My proposed solution costs below 300 ringgit, and if this product is brought to the market, the scale of manufacturing can further bring down the unit cost. Ultimately, this would allow more users to purchase and use this product at the comfort of their own homes. So now I will show a really quick demo video on the real-time prediction aspect of this project. This video demonstrates the different objects that this glove can recognize with an SVM-based machine learning algorithm. The confusion matrix shows that this algorithm can assist the glove in recognizing objects with an accuracy of around 91.8%. The high accuracy aspect of this project shows great promise in the application of rehabilitation, as it means that the data can be used to track improvements of the user over time. For example, the data collected can show an improvement of the user's hand function as well as the highest improvement of grip strength of each finger. In addition, this glove can also provide an educated guess on which exercise regimen is the most effective for any particular user. In closing, neurological diseases that affects the motor skills such as stroke or Parkinson's disease affects more than 2 million people annually in the United States alone. I am confident that the impact that this solution may bring to the world of rehabilitation will be one that is both affordable and sustainable. Thank you.
Okay, so that was the video. Okay, so I hope you enjoyed the short demo video about why I'm so passionate about this project and how this solution that I've designed has shown great promise in the world of rehabilitation. So this video has provided some context on why a stroke or an Alzheimer's patient would want to integrate this solution in their rehabilitation training. But that's just one side of the story. What this video does not demonstrate is why a physician would want to recommend this to their patients. After all, if a physician or a physiotherapist doesn't want to recommend this to their patients, no one would use this product, right? So in the next part of this presentation, I would like to demonstrate on the data that a physician will be able to see on one of their users using this product. So to do that, I'll have to share my screen again. Okay, hopefully you guys can see the screen. So this is a website that I've created for this project, and it shows the patient's dashboard. So for example, this is patient access dashboard. So through the data obtained from the glove, you can create statistics like this. For example, you can see the performance chart of patient X. From here, you can tell the bar chart, which is the average monthly grip strength, and the line chart, which is the improvement of the user. So as a physician, at one glance, you can tell whether a patient is improving or not in the long run. And this is only possible because the glove is tracking the patient's rehabilitation exercises through the machine learning algorithm. Okay, the next thing here is we have the radar chart. Okay, so the radar chart is another representation of improvement, which is another measure, but this is more specific. So you can see each of these points here. We have the distal interphalangeal, the proximal interphalangeal, the metacarpophalangeal, the joint flexion, and the finger responsiveness. So these 5 points are the measures of joint movement. The distal interphalangeal, proximal, and metacarpophalangeal joint are the 3 joints of your finger. And through this graph, each line represents 1 finger, as you can see here. And so you can compare between 2 fingers. For example, if I want to compare between the ring and the pinky finger, you can see that from here, the ring finger has a higher joint flexion compared to the pinky finger, and also a higher distal interphalangeal joint movement. So from this chart here, you can tell that which finger needs more training, and it is also a measure to decide whether a certain rehabilitation routine or exercise should be changed based on how well the finger is responding. So the next thing here is a glove input data. Unfortunately, I do not have the glove with me right now, but this is supposed to transmit the real-time data from the glove. So what I can do is just a simulation. So this is what the glove or what the physician would see when the user is using the glove. So when the user is not holding any objects, and each line represents 1 finger. So this is what they will see when the user is holding a cuboidal object, a cylindrical object, and a spherical object. So all this is true data from the machine learning algorithm that I've just taken 1 sample of. So for the final one is a send message to patient X function. So I truly believe for rehabilitation to work, there has to be a 2-way communication. So the user has to provide data for the physician to work with, and the physician, of course, has to respond or have to feedback to the user. That's how rehabilitation works. So in this case, this is what I've set up. It's a send message to patient X. Maybe I would like to ask the judge to help me out a bit in this context. Maybe I can ask Mr. Wong Ming Wei. Maybe you can help me out a bit.
Yeah, sure.
Okay, so what I have here is, okay, can you visit this website here? I can paste this in the chat.
Okay, sure.
Okay, so what I have here is I have set up an LCD screen. Not sure if you can see. And whatever is sent through this box here will be transmitted to the LCD screen. So Mr. Wong, can you pretend that you are a physician for today, and I'm patient X, okay? So you have been seeing that my improvement that my performance has been improving. So maybe you can type a well done message or a congratulations message and press submit. And I will, not sure if the camera can catch it, but I will show the camera whatever is typed. Or maybe I can just read it out.
Okay, let me do it now.
Okay.
Okay, I just submitted.
Okay. Not sure if you can see. You type.
Not really, Chu Chen. You have to read it out.
Okay, okay. So Mr. Wong typed, "You are making great progress."
Correct. Yeah.
Right?
Yeah.
Yep. Okay, so that was just a very quick demonstration to prove that this glove can actually work anywhere in the world. So the patient could be in KL while the physician could be in Penang or Malacca or Johor, and it wouldn't matter because the data provided is sent through the internet. So this also means that rehabilitation centers do not have to limit themselves on finding clients from one specific area and can look for clients all over the country. This has the potential to increase the client base of the centers. So in conclusion, I truly believe that this IoT-enabled smart glove has the potential to change the world of rehabilitation. So that's all for my presentation. Thank you so much for listening, and I hope you enjoyed this short demonstration.
Thanks. So let us invite Q&A sessions from the judges.
Let me get started. Is it the size of a hand for different people or even between male and female are different, right? So your glove, is it universal or does it need to be recalibrated for different user?
It's universal because everything is being trained through a machine learning algorithm. So whatever data you provide it, then it will run according to that. And also the joint is let me share the screen again. Yeah. So not sure if you can see that. So this is what the glove actually looks like.
Yeah, I can see.
Okay.
And how frequent the sensor need to be calibrated or characterized?
So far, I've only characterized it once, and it has made the same predictions throughout the entire project. So I'm not too sure how often you need to characterize it.
All right, thanks.
Hi, Jujen.
Hi.
I'm Huyen.
Oh, hi.
Hi, thank you for sharing your project, especially when you share your story about the inspiration that you have to start the project with. My question to you would be, were there any, did you explore if the AI glove is able to perform an self-learning, such as placing an unknown object and then it determines the shape? Because currently what you're doing is that you put a known object and then you program to define what's the shape. So the question will be, is it able to self-learn since it has AI capability?
Okay. To your question, have I explored through it? I have not really touched on the recognizing objects where I have not defined it, but I'm sure that it can be done, mainly because as long as you provide it enough data, it can find conclusions based on those data. Does that answer your question?
Okay, thank you.
Okay.
Hi, Chuchen, it's Chia.
Yes, hi.
So I understand that you mentioned this device will have a continuous machine learning in progress, right? Or it's just only done once and user can just use it without connecting to any devices.
Can you repeat the
what I
question?
mean that when the user want to use your device,
yes,
does he need to connect to a computer in order to carry out the machine learning, or it doesn't need to?
Yes, in my case, for this prototype, you need to connect to a computer.
Okay, so in order for it to make it, more flexible or more easy to use for others,
Okay.
so can you use it on a mobile device? Will a mobile device powerful enough to carry out all your machine learning algorithm?
Yes, because the training only needs to be done once. And once the training is done, you can export this training, whatever is trained, into a mobile device or a device with less computing power, because the training has already been completed.
Oh, okay, thank you.
Okay.
Hi, Chuchen. Jessie
Yes.
here. What are some of your key challenges in your design, and how do you overcome them?
Key challenges. So meaning, what are the problems that I face? Is it?
Yeah.
Okay. So to start, right? I'm not that good in machine learning, so this was a whole new world to me. So I had to start from the 3 months of because this is my final year project. So from the 3 months of the final year project, I had to learn machine learning, and I had to train myself basically on how to use this machine learning thing. And so to overcome that, it's just a lot of persistence, basically a lot of trial and failure, and you just have to keep trying.
Okay.
All right, anybody else? Any question?
Julia here. I think you just answered my question. I was going to ask you how you learn about machine learning. So I guess it's on your own, and
Yes.
that's a very good attitude.
Thank you. Thank you.
Great job.
Thank you.
Yeah, is there any further questions? If no, I would like to invite judges to comment on the projects.
Yeah, I'm interested in the way this design is simplistic, and also the cost is quite minimal. I think for 300 ringgit, most people can afford it and put this at their home. And given that, especially during this time, during COVID, to go to hospital or rehabilitation center is be quite dangerous, I would say. So if we have this at home, it will be it's a great tool to have, especially those people that requires a regular training to ensure they can speed up their recovery. It's a very practical project. I think you, with the real time, monitoring and real time progress update to the patient, I think you encourage the patient to, do more training. I guess, I think in overall perspective, this has a great commercialization opportunity, right? I think you should push further by, trying to pitch this to maybe venture capitalists or something. Right? Okay. Great work overall. Thank you for the
comments.
sharing.
Okay, thanks comment from the judges and also Mr. Lims for your nice presentations.
Welcome.
All right, let us welcome the third teams from University Technical Malaysia Melaka, UTEM, with the project's ID MY110. Titles: Developments of Myoelectric Muscle Sensor with IoT Technology for Continuous Predictions of User Motions Intentions. These projects were presented by Lee Leong Jings and Chan Hua Sings, and supervised by Dr. Nora Fizals binti Abbas, and also Professor Marias Dr. Muhammad Shahrus bin Muhammad Aras. So Mr. Lee, the floor is yours.
Hey, hello. Hi, good morning to all the judges. Hello, can you guys hear me?
Yes.
Yes.
Okay, so I may begin my sharing now. Before that, could you guys please turn off your video, because it may affect the bandwidth, as my area here has a poor connections of the internet. Okay,
Sure.
thank you. Okay, so I may begin my sharing. So I will like to start my sharing now. Okay. Yeah. Okay. So can you guys see my screen actually? I hope
Yeah.
you guys do. Okay, so let's begin with the introduction of my projects. So the background of the project is based on a study. According to the latest Institute for Health Matrices and Evaluation data published in 2020, so stroke is the top 3 leading causes of death in Malaysia from 2009 to 2019, as shown in figure 1.1 here. Okay, although stroke is the top 3 leading cause of death in Malaysia, but there are a lot of people who survive stroke, shown in figure 1.2, where it is the most 62% cases registered for dormitory healthcare services. Okay, people who survive stroke, they need to undergo rehabilitation to regain their speech, cognitive, motor, or sensory skills. And rehabilitation program for stroke often involve the training of strength, mobility, and range of motion exercises, which are monitored by utilizing the EMG signals. The EMG signals will record the electrical potential generated during muscle contraction, and thus the properties of EMG signal are useful for doctors to keep track and evaluate the process in stroke rehabilitation of patients to ensure a fast and efficient recovery. These are my motivations. So according to a survey performed in 2018, it is observed that the rehabilitation services provided within the state of Selangor and federal territories of Kuala Lumpur is distributed unevenly, especially for the population of urban poor and people in the rural areas. The cost for development, construction, and manpower will be high to set up new healthcare facilities. So an alternative solution should be considered, such as the use of a home-based virtual rehabilitation program. And to visualize this conception, the idea of designing a myoelectric circuit for user motion intention with IoT application is inspired. This development would be able to help doctor to monitor the patient recovery progress from a distance. The developed circuit can also utilize as a control signal for prosthetic hand, such as the prosthetic hands, arms, and lower limbs to achieve human-machine interactions. Okay, then okay, so for the problem statement, the increase in stroke will lead to the increased demand in rehabilitation or assistive device. User motion intention need to be considered to robustly control the device. The input signals need to be linear envelope for it to control the assistive device. However, most of the EMG signals are non-linear and require a circuit to process it. In addition, by adapting IoT into the EMG circuit will ease the process for data collection and enable physicians to monitor the recovery of a patient from a distance. The objective for my project is to design a myoelectric circuit for detection of user motion intention with IoT application, and then to establish relationship with forearm EMG signal with different hand grip force and wrist position using the design circuit, and finally to analyze the design circuit in terms of accuracy and mean absolute error MAE. There are 3 project scope for my project, where all the subjects are normally limb with no previous or present muscular injuries or diseases, and the electrode used in this experiment is subjected to surface electrode only, which will not cause harm to subject. And the design circuit is validated using the data collected by previous researcher using the EMG device by Vernier, where the established relationships are compared and analyzed. Okay, so let's move on to the literature review part. So here is the EMG signals, how you get the EMG signals. So EMG signals are actually electrical potential generated due to the voluntary muscle contraction, and is sometimes referred as the myoelectric activity. This signal is normally a function of time and is described in terms of its amplitude, frequency, and phase. So here is the anthological and physical background of the motor units. And this is the comparison of the myoelectric detection circuit, which I had contemplated based on a few past research paper, where I list out all the disadvantages and also the advantages. So by completing the disadvantages and also the advantages, I get to design my own circuit. Okay, so okay, we move on to the methodology part. Okay, so for the methodology part, I start off with the literature review. So after I conducting the literature review by the gap analysis between previous research paper, so I came to the designing of the myoelectric condition circuit. And then I run the simulation of the design signal conditioning circuit in multi-sim. And if the result generator is desired, then I begin with the construction phase. And then after the construction phase, we will go through the myoelectric circuit proof of analysis. If the signal generator is desired, then we will move on to design the myoelectric sensor with the IoT interface and integrate the multimodal sensor fusion, which are the EMG signal, the self-developed hand dynamometer and wrist angle readings with the IoT technology. Then we will select the forearm muscles and testing by collecting the data of forearm EMG signal, and then we will establish the relationship with forearm EMG signal, different hand grip force and wrist position using the design circuit, and we will do the overall system testing. And if the performance is desired, then we will evaluate and analyze the performance in terms of the accuracy and MAE. Okay, then at here we have the overall system architecture. So as you can see here, this is the forearm muscles. So this is where we place the electrode. And then after that, we will get the EMG conditioning, and then we will do the circuit testing using the Keysight 2701A USB modular oscilloscope. And then after it has been validated, then we will pair those other sensors such as the accelerometer and the hand dynamometer sensor with the Raspberry Pi. Then the data will be stored in cloud. So at here is the block diagram for the EMG conditioning that I designed. Okay, so this is the input. Here is the raw EMG signals, and this is the sensors that I used, which is the AGCL electrodes. And then all of these signals will be go into this circuit element, which is the instrument amplifier. So the instrument amplifier is used to amplify the voltage, and then the signal will also go to the driven right leg circuit, which is used to increase the signal to noise ratio by having the signals point to the ground, which refer to the bony part of our body segment. After that, from the output of the instrument amplifier, we will go to the high-pass filter here. So the high-pass filter is used to eliminate the low-frequency noises caused by the motion artifacts at 20 Hz at -3 dB. This is what I designed. And then we'll post to the low-pass filter to eliminate the high-frequency noises, which are caused by the inherent of the electronic noises at 500 Hz at -3 dB. Okay, then the signal will pass to the two-way rectifier to produce the linear envelope, and then it will go to the smoother to smoothen the signals, and also the inverting amplifier and optocoupler. The optocoupler is to provide the biosafetiness to the subjects. So at here we have the circuit simulation. Okay, and then at here is the block diagram for the myoelectric sensor with the IoT interface. So at here we have the multi-sensor model fusions, and then it is paired into the Arduino Uno. And then the signal will go to the Raspberry Pi. The Raspberry Pi will act as an internet gateway to transmit the data into the laptop and also the smartphone. So the laptop and smartphone here is act as the data analytic and user interfaces. So we move on to the result and discussions. So basically, this is the constructed myoelectric detection circuit based on the simulation in the multi-sim. Okay, so next, okay, so this is the circuit testing which I had done using the Keysight modular oscilloscope and function generator to validate the data. Okay, so these are the troubleshootings. So for the input, I use 50 mVVP at 100 Hz because normally human biosignals is at 10 milliwatt, but I use 50 milliwatt VVP. So here are the results. So if you can see, here got some noises, but it's okay because we got the high-pass filter and also the low-pass filter and also the DRL circuit to eliminate all the noises to get what we desired. So at here, we got the, this is the output from the two-way rectifier. Okay, as you can see, the noise is eliminated. So the signal has become more smoother. Okay, then this is the construction on the PCB. Okay, so why I did the construction on the PCB instead of used before one. This is because when we do the circuit testing, everything is fine, but when we interface with the muscles, then there is where the problem occur. Because when we interface with the muscles, right, because due to too long the wires that we use in here may be too long, here may be too long for the input. So it will affect the DC offsets. If the DC offset is too high, then when you get the signals into the oscilloscope, then because we got the instrument amplifier, so instrument amplifier eventually it will amplify the voltages. So when it amplifies the voltages, it also amplify the DC offset. So by doing the construction on the PCB, eventually we will eliminate the effect of the DC offset at a very large scale. Okay, next we move on to the hand grip force measurements and also the wrist angle measurement. So here is the hand grip force measurement for the self-developed hand dynamometer. So as you can see here, this is the hand grip force measurement for the neutral and also the deflection results. So as you can see, for deflection, the subject is hard to remain. The subject releases instantaneously. So that will cause the sensors to be not held in the same position because the subject released instantaneously. So the percentage of MVC drops below 0%. So okay, we move on to the wrist angle first. Later got question you guys can ask. Then for the wrist angle measurement here, this is the wrist angle for the neutral position, which are supposed to be at 0. And this is the wrist angle measurement for the flexions, which is supposed to be at 45. Okay, so this, as you can see here, this one occur because when the subject tends to exerts the force to grip the hand dynamometer, then it's found that the subject is very hard to when you are using force, it's very hard to maintain the posture. So when you are exerting force, so as you can see here, the value drops by a bit. Okay, then this is the overall experimental setup. Okay, so here is the electrode patches, which is then connected to the design of the microelectric circuit. And here we have the wrist angle measurement, which are using the flex sensor, and at here we also have the hand dynamometer. So all of these is connected into the Arduino Uno. Then the data is sent into the Raspberry Pi, just like what I mentioned just now. The Raspberry Pi acts as an internal gateway, and then the data will be then stored in the cloud. So as you can see here, there is no connection between my laptop and this overall circuit. Okay, then we move on to the not-read flow, which is used inside the Raspberry Pi. If you don't know what is not-read, then not-read, let me tell you, is not-read is actually a software which are embedded in the Raspberry Pi. So at here we have the not-read flow. So here it is serial connected from here. It is serial connected from the Arduino, and then it goes into a replace area for every functions and also the CSV file, and then we will have all the data displayed here. So here is the gauge node, and also we have the HTTP request to send the data to the cloud. Okay.
Yeah, Mr. Lee, The time is up. So may you go to the last page to conclude your overall projects?
Okay, sure. Okay, so in conclusion, actually all the data is stored in cloud. So if you want to retrieve it, you can get all the data from the ThinkSpot server here. And also, yeah, still got more to cover, but never mind. So in conclusion, the overall product for further improvement or further adaptation, we could use the surface mount technology, and also we could adapt the ANN into my project, and also finally we could adapt the EMG signal to the game. Thank you.
Thanks. So I would like to invite judges for the comments.
Yeah, Leon Jing, one question from me is regarding to, your project is divided into 3 phases, right?
Yes.
Which one is the most challenging and time consuming?
Of course, the development of the myoelectric detection circuit is not easy to construct a sensor.
And in your design, during your demonstration, I think you need to place the myoelectric sensor right on the arm. Yeah, you need to place the electrode patches, right?
Yes.
On the arm. So have you ever thought of maybe putting how to make sure they put it properly? Does the placement cause a variation in readings?
Yes, it does. Okay, so this EMG device is quite sensitive. Okay, so for your knowledge, different muscles will contribute to different actions. Okay, so what we are investigating here is the wrist angle measurement and also the hand grip force measurement. So for this, the muscles that are highly responsible for this action is known as the FDS muscle. Okay. So I actually got here FDS muscle, flexor diaphragm superficialis muscles. So this is actually the locations of the FDS muscles which are contributing to these actions. Okay, so how we determine the muscles where do we know where exactly is the muscles? So this is how we determine it. So we place our forearm on the shoulder. So when we are trying to when we do the when we are flexing the both of the 3 ends of the muscles, then we will feel the muscles bellies, which is actually located here. So at here, this is the place that we know where to place the electrode. Then both of the electrode pages need to be placed as close as each others, because this would if it's placed too far, then it will affect the CMRR ratios. It will affect the signal quality to be common.
Okay, in your paper, you also mentioned about using the artificial neural network, right? So can you please elaborate why this is needed since you are collecting real-time data?
Okay, good question. Okay, this is because why we use ANN. Just like I got also mentioned, right? Because there are different muscles which are contributing to different actions. Okay, so by using the ANN, okay, when we place the electrode pages here, okay, because sometimes different people got sometimes their form is quite huge, and then the muscles the size of the muscle is also not the same. Okay, then by using this, okay, so by using this using the ANN, we are able to determine which muscles precisely that contribute to the actions. Okay.
All right, thanks.
Okay, any more questions?
Youngjin, hi.
Hi.
Hi, Ian here. Yes, so thank you for sharing. Very good project, very details and very technical. My question is, can you elaborate more on how the information that you have gathered from the measurement is translated into useful information for end user? And what action can be carried out after the end user get the information? Can you just elaborate a little bit more on this part?
Okay, sure. Okay, so I continue cover my result part. Actually, that is on my result part, but I didn't manage to finish presenting. Okay. So here is the data collection and analysis part, for the collected data. Okay. So we got the EMG masses, which just now I mentioned in my project scope, right? We are referring to the EMG device by the vernier. So if you can see here, so when this thing, when we like exert the force, okay, you can see when we exert the force, the force is increases, right? So the EMG muscle sensors we also show increases in values, right? Okay, so so this is the angles. Then we move on to this one here. Later I move back. Okay, so if you can see from here, okay, the data collection. This is the mean absolute area computed for each measurement unit. Okay, if you can see here, why it is useful. Okay, so this is actually known as the multimodal sensor fusions. Why we use the multi-sensor modal fusions? Because sensors, right, when we tend to use the sensors, so sometimes there are a loss of data. Do you agree with me? There are a loss of data in the sensors. So when we are using the multimodal sensors, right? Okay, so if you can see here, so this is the linear envelope EMG signal, hand grip force measurement, wrist angle measurement, as compared with the at the minimum hand grip force. If you can see here, if these values, right? Okay, if these values, okay, it is of this value actually has the linear relationships between each other. So if you notice this value increases. Okay, so at here this value also increases. We will know what will be the we will know what will when will be the calibration we need to do, because if like here we got the loss of data, because this if you comparing, right, so this one we have a quite huge error at here. So for sure this error also must be big, right? So if this error suddenly drops, then we know we need to do the calibration. And also when we are implementing the multimodal sensors, when one of the sensors data is lost, there are other sensor data which are able to back up the other data, to back up the data from other sensors. Okay. So just now you asked me, right, what actually the users are. Okay, so how the users know. So at here, as I mentioned, so the hand grip force and the hand grip force and the muscle signals actually they are both in a linear relationship. Okay, when the force increases, so as the muscle sensors value increases. Okay.
Right. Thanks, Mr. Lee, because we have run out of time. So may I invite panel from Keysight to give comments for the overall projects?
Okay.
Yeah, this overall this project is well designed and validated. I think from technical perspective, you and your team has put in a lot of effort and have done a great job. Okay, from design and user friendliness perspective, I think you may want to improve the prototype to be more intuitive. If let's say the end user is to, well, I don't know who is your target so-called user. If it is for the home patient to use it, the placement of the patches or sensors on the arm may create a lot of variation depending how they use it. But if it's not meant for the home user, I think it's still okay. So overall, it is a good project. I think it can be have potential to be used by professional caregiver or practitioner, right? So good job overall. Thank you.
Okay, thank you very much, Wei. Ming, Wei, thank you very much.
Okay. You're welcome.
Right, thanks, thanks comment from judges. So I'm sure those comments are going to help the projects. And thanks, Mr. Lee, for your nice presentations.
Okay, thank you very much, Mr. Chi.
I would like to invite the fourth teams from International Islamic Universities, Malaysia, IIUMs, with the project's ID MY233. The titles of these groups: geofencing location tracking systems using IoT and LoRaWANs for COVID-19's mandatory self-quarantine monitoring. It will be presented by Muhammad Hafizi bin Abdul Malik, supervised by Associate Professor IR Dr. Siti Fauzia Toha and IR Dr. Ahmad Sharin Idris. Mr. Muhammad Hafizi, the floor is yours.
Thank you. So I will present my slide first. So everyone can see my slide, right?
Yes, we can.
Yes, we can.
Okay, thank you. So, so I will start. Okay, again, and hi and good morning. So my name is Hafizi from International Islamic University Malaysia, Group MY233. Our project is about geofencing location tracking system using IoT and LoRa for COVID-19 mandatory self-quarantine monitoring, supervised by Dr. Fauzan and Dr. Sharin. So before we start, I would like to go through the contents of my presentation today, begin with the problem statement and the current implementation. Then we will discuss about our solution. After that, the technical details of our solution as well as the prototype builds. Lastly, I will talk about the post-COVID-19 use cases and also the conclusion. So, as we all know that we have been living with COVID-19 for 1.5 years already, and we can see the number has been increasing. Even last week, Malaysia recorded the highest daily new cases for around 17,786 cases, nearly 18,000. And we also have recorded the highest number of deaths, around 207 death cases in 2 consecutive days. Despite we're having a good rollout for vaccination program, latest data show that vaccinated individuals can still be infected by COVID-19. So why are infections still increasing? So the first thing is because due to new variants, such as the Delta variants, so the patient seems to produce 1,000 times more viral particles, make it more likely to expose to other people, and it works airborne. Second, it is made due to many non-adherence to SOPs. So quarantine is necessary to break the chain of COVID-19 infections, and it must be done for 10 to 14 days at least. There have been numerous cases such as Sivanganga cluster in Kedah and also Itali cluster in Sarawak, which have led to many deaths. And as we all know, Malaysia established self-quarantine by using color-coded wristband. However, some individuals refuse to comply the current self-quarantine rules and are moving around in society. Moreover, some of them are able to hide their quarantine bracelet while being outside. So this happened because the current implementation requires manual observation on the wearer position, and authorities are not easily alerted to the non-compliance. And also, the wristband cannot be identified automatically. For other countries, there are some which have implemented electronic device, such as Hong Kong and Dubai. And however, some limitations are identified. For example, for Hong Kong, it needs a secondary device such as a smartphone, as well as the internet connection, and also requires scanning QR code regularly to update on wear status. As for Dubai, the wristband requires charging twice a day, and it is fixed to one single location. So for other implementation, will be in a smartphone app-based, and of course, it requires smartphone and also internet connection. And the user also need to charge the device or smartphone on the daily basis, and most of the apps require the user to log in or take selfie periodically. So our solution, in order to overcome the limitations, we propose an electronic device that can ensure that individuals stay at their safe quarantine location, ensure that the device cannot be taken off during self quarantine, and then able to communicate status of individual to the authorities, and able to work during the entire self-quarantine period. So for this, we implement electronic geofencing with status detection, wireless communication, and low power consumption. So this is our solution, CAGE, stand for COVID-19 adherence via geofencing tracking. So we want to make CAGE as easy to use for the end user as possible. The user just need to put it on, turn it on, and keep it staying on their wrist and ensure that they adhere to self-quarantine. So in terms of simplicity, the end user does not need to do anything. In terms of usability, we want to ensure that it has low power consumption so that CAGE can last throughout the self-quarantine period. In terms of flexibility, we want the authorities can check on adherence to self-quarantine from anywhere. For usability, we hope that the device can be reused or reset for the next users. So before we proceed to the technical detail, I would like to highlight the project timeline through our IMDC. We started at the beginning of December 2020 after accepted for Keysight technology track and CRISE. We built our first version, our first prototype of CAGE, and the result were presented during the midpoint clinic to Keysight and CRISE panels, received many useful comments and come up with the second version. And then the result was used for paper and video submission. And then we had a strict MCO, as we all know. However, we did manage to present the second version and in June 2021 for the first judging session. And we received for the useful comment, and then here we are for the grand final. So for CAGE V1, to develop CAGE V1, we had a few objectives, but before that, CAGE V1 was built on 4 major components as shown in this slide. The first one is Arduino Uno, GPS module, LCD, and also LoRa shield. And together were to send the data to the Things networks, the cloud server. So our first objective is to implement geofencing algorithm. We want to acquire location data from GPS, and then we process the GPS data and apply geofencing algorithm to check if individual is within boundary or not. And the second objective is we want to implement security fuse function. So we make one IO pin to check the status using interrupt function, and the status cannot be reset by the user. So once the wristband is disconnected, the user cannot reset the status by putting it back together. So third is we implement a wireless communication. So the geofence data and security fuse data we send via LoRa wireless communication. So the data will be received and can be checked on the Things networks, aka the cloud server. So to be highlighted, for confidentiality purpose, all data are processed on device and all the status are communicated via LoRa to cloud server. So here, there are no detailed data will be exposed to the authority or to the public, such as the exact location of the user. So for CAGE V1, on the left side, it shows the initial build of CAGE V1 and all components were put together. And on the middle, this is the basic flowchart for the whole device operation. And also we have tested and validated our program and result at several locations, double-story terrace house, standard house, dormitory on ground floor, and also dormitory on 4th floor. And what we found out that in terms of precision, GPS location precision is tested to be within plus minus 3M compared to smartphone GPS. So, and then in terms of CAGE accuracy, sometimes GPS signal sometimes drifted and measured to be plus minus 7 meters. And for our case, we set the geofence boundary limit to 30 meters, but of course, it can be adjusted for different quarantine locations. And then this is an example how data being received to the Things network, the cloud server. It shows device where status, connected or disconnected, and then as well as the user position status in or out. So this is basically the data we send to the Things network. So we can verify the individuals is adhering to self-quarantine or not. We can check if the individual is still within boundary and the CAGE has been removed or not. So at this stage, the objective of for geofencing security fuse and also wireless communications have been met. And this is completed CAGE version 1. All components were simply put into a cardboard box and powered by a power bank. So the total cost is around 150. So this is the dimension and the weight of the device. So in terms of objective, from our case version 1, we got the geofencing, security, and also wireless communication through LoRa. But we look at the case V1, it is not wearable because the size is quite big and it is powered by a power bank and has a high power consumption, which could only last for around 1 day. So due to the limitations, we developed the second version of prototype build. We look into integrated development board, which is a TTGO-TB LoRa board. It has integrated new system GPS module and also LoRa module. And then we put on OLED display. It is also based on battery power. For our case, rechargeable LiPo battery is used here, 3000 mAh. And for that, we provide a 3D printed case and wristband for it to be wearable. So as shown on the right figures, how cage can be worn, and it can be easily put on the wrist with the help of magnet metal clamp, so magnet metal clamps. And then the security fuse work as it is connected when the metal clamp put together. So along the wristband, you see on the right bottom figures. So along the wristband, it is incorporated with the security fuse. So if the metal clamp is touched together, so it means the security fuse is connected. And then the main advantage of second version is that we are able to optimize sleep mode duration and also minimize the idle current. So for case V2, we are able to reduce active and idle current and using 3000 milliamp ampere LiPo battery. The battery life can be extended to around 12.5 days as case V2 is also wearable. So we also did test that cage can be 5 km in distance from the LoRa gateway. So this is the completed case V2. So the total cost is about 140 ringgit. The dimension is smaller compared to V1 version 1, and the weight also has been reduced. So case V1 did improve compared to previous version as it can be wearable with a 3D printed case, and it also has a lower power consumption and while running on battery power. So because of the battery power that it can be rechargeable and make it to be reusable. However, the comment received during the midpoint credits indicate that the size is still a bit big and the external antenna make it less suitable or less comfortable to be worn. So from these comments, we started working on case V3. However, we are not able to develop a proper 3D printed case due to restricted MCO days. So case V3 consists of smaller development board and Heltec LoRa development board was chosen. So again, it has an integrated LoRa module and we can attach external Neosys and GPS module and also a LED display. And the advantage of this development LoRa board, so is that it provide a flexible antenna. So on the right figure, so we can see the prototype build of case V3. As you notice, the design is still in progress. So the total cost came out to be cheaper as the dimension and weight are smaller and lighter compared to the V2 respectively. So I show you like so this is case V2. We have it here, and then this one is you can see from the camera, right? So this is case V2 and this is case V3. You see the size of V3 is slightly smaller than V2 and perhaps it's more wearable for our project. So the objective have been made as it able to geofencing, and we can add a security fuse and we can communicate through LoRa wirelessly. And the device also provide a low power consumption, make it wearable as well as be reusable for the next users. So throughout the development process, we try to ensure that cage will be very easy for the end user to use or handle. So they just need to put it on, turn it on, and keep it staying on their wrist for the whole self-quarantine period. So the cage also we want to ease the authorities so that they can easily check the adherence of the high-risk individuals. So for the COVID-19 use cases, post-COVID-19 use cases, we came out with 5 different scenarios where cage can be implemented. First, for patient monitoring system. Second, for child safety at schools. Third, for workplace time tracking, especially for hazardous occupations. And fourth, for prison parole system used for governmental agencies. Fifth, for permissive tracking, especially for those who handle the harsh activities. So these are the 5 different scenarios we can implement at the post-COVID-19 use cases. So in conclusions, to be highlighted, we have still not won the war against COVID-19. Even after 1.5 years, the COVID-19 situation seems to be getting worse rather than better. We hope that an industrial partner or governmental agencies can help our idea to ensure that strict adherence to self-quarantine is implemented so that we can break the chain infection and get back to normal. And I will end my presentation with a thank you to Keysight Technologies, CRISE, and also IMDC 2021, and also my supervisors, Dr. Fawzi and Dr. Sharif from IUM University, Sarawak, Malaysia. So thank you very much. I will welcome any question that you have regarding my project. Okay, thank you.
Thanks. So I'd like to invite judges for the Q&A sessions.
Hi, Afizi. This is
Hi.
Jessie here. Great job and great design and the use case you have for your project. My question is, I see that you have improved on your design to the KHV3 finally, and it has reduced the size and the weight quite significantly, right? So great job on that. How about the battery life? From your V2 cage, right? It was 12.5 days. So what is your KHV3 battery life status right now? Is there any
Yes.
improvement on that?
For now,
That you forgot to share or didn't mention at all just now?
okay, I mentioned actually for the KF3 we cannot test it fully. We are not fully tested, so we expected that the current consumption by the V3 is to be similar like the cage V2, since the detail of based on the data sheet of the new LoRa board, the HealthTech one, so it's quite similar to the previous version. So then, however, for right now, we only have a 1,000 milliamps compared to the second versions, which is 3,000. So the current consumption is similar to V2, but then for our current prototype for V3, it may last for 1/3 of the days, like a version 2. Sorry. Is that answer your question?
Okay, so the conclusion is about similar battery life as version 2. Right?
Yes.
Okay,
Yes.
thank you so much.
Hi, Afizi.
Hi.
Hi. So this is Maya here. So good project at the right time. So, and I see you clearly mentioned what else, where else you can use this other than for COVID. So great job there. So my question is also a bit related to what Jesse asked. So I see you mentioned improvement, right, on the power consumption from cage 1 to cage 2.
Yes.
So is that purely because of your change of battery, or is there any improvement in your design that
Actually,
made the power consumption is lower?
Yeah, based on the comment received from the midpoint clinics, the only thing that we can do to reduce the current consumption is that we have to change the development board. So from the first version, you can see that we use the Arduino, but then from the whole components, we use the wired connections. So when we change to the integrated development board, so the distance between the components and the components is become smaller or lesser. So then the current consumption can be reduced from that. So based on the comment received, the only thing to change the current consumption greatly. So we just need to change the development board from one to another. That's all, to reduce the current consumption.
Okay, so good to hear that you improve from the feedback from the midpoint clinic. Great job.
Thank you.
Is your V3 waterproof or not?
Yes, that I want to highlight actually. So we want to make sure that if we want to implement it immediately, so we want to make sure that it's waterproof. For now, all versions is not waterproof. So if you want to immediate implementation, so we want to make sure that for the real life, it has to be waterproof so that they can use the device on the daily basis. So for now, all versions are not waterproof.
Okay.
Afizi, this is Julia here.
Yeah.
I'm thinking from the point of commercialization. You know, people are very sensitive with telecommunication tower near your house, antenna near you. So if
Yeah.
I were to ask you, how do you convince the community that this is safe? What will you do? What will you say?
Again, may I know in terms of safety, what aspects? I mean,
People
from
are very sensitive when antennas are near them,
oh,
generally. And
I
the
see
longer
that.
the antenna, the bigger it is, the more worried they are.
Yeah.
So how would you address this question?
Yeah, as you can see from the version V3, essentially we use a flexible antenna. So the flexible antenna will be integrated into the wristband. So when it's integrated wristband, it's basically the users uh, cannot notice the antenna in the wristband compared to the V3. So that's one solution that we propose to make sure that the user will not wonder whether they are notice about that or not, something like that lah. So other thing is if they are asking about the antenna, I mean about the privacy or safety. So maybe we need to make an announcement or something like that announcement so that we can emphasize that the only data we are sharing through the cloud server is only their status. Well, there are no exact location, like I said before, there's no exact location shared to the cloud server.
Right. Thank you.
Okay, thank you.
Right, thanks. If there's no further question from judges, so may I invite Judge to comment for the overall project?
Yeah, this project is definitely very timely, given the never-ending COVID cases in Malaysia.
Yeah.
The pink tag is clearly proven to be not effective, right?
Yeah, sure.
Yeah, I hope you can pitch this to KKM, at least try this out,
Okay.
for those quarantine, candidates.
Okay.
And if you can downsize this further and make it waterproof, or perhaps make your design having the features of battery changeover without having any downtime, I think the application of this device is limitless, right?
Okay. Thank you.
I'm looking forward to one day, very soon in the future, to see this device being used across Malaysia. All right.
Hopefully.
So good
Okay.
project. Thank you.
Okay. Thank you.
Great job, Hafizi.
Okay, thank you.
Okay, thanks for the comments from the panels, and thanks Hafizi for your nice presentations. Lastly, I would like to invite the final teams, the 5th team from University Technicals Malaysia Melaka, UTM, with the project's ID MY239. The titles for the projects: Design of an Automated Illuminated Emergency Exit Door Systems, which will be presented by Wei Qingyi, Xiao Wei Hao, Cham Yong Jun, supervised by Dr. Siva Kumar, Anat Laki Subramaniams. So, Qingyi, the floor is yours.
Okay, let me share my screen first.
Yeah, sure.
Can everyone see my screen?
Yes.
Yes, we can.
When Okay. Is my voice clear?
Yes.
Yes, perfect.
Okay, I will start my presentation now. Good morning, everyone. I'm Wei Jingyi, and I'm going to present our project entitled Design of an Automated Illuminated Emergency Exit Door System, Auto IEED, on today. The basic design concept of this project is about the emergency exit door integrated together with the directions and signal light. For your information, this presentation is divided into 2 sections. Part 1 is about the elevator pitch, and Part 2 is the technical presentations. I would like to start by looking at the problem statement. Firstly, curious on emergency exit door location. Occupants are new to the building structure and curious on the location of emergency exit door during their first visit to a building. So during a fire event, they have no idea on the safest door to get out of the building. Secondly, invisibility of conventional exit sign. In a building fire events, occupants are distracted with thick smoke and carbon dioxide fumes. The use of conventional exit sign is insufficient to guide the occupant from safety. Well, this situation becomes even critical in a multi-storage building. This will result in an unguaranteed evacuation. Thirdly, curious on other side of emergency exit door. In a building fire events, occupants get panics and look for an emergency exit door. However, by simply entering an exit door might put their life at risk because they have no clue of what lies on the other side of the door. This will greatly threaten someone in such chaos. I believe everyone is familiar with this. This is the exit sign we notice in all public buildings in Malaysia. It simply denotes the location of the closest emergency exit door without providing any guidance in case of fire or other emergency that require evacuation. For this reason, my project is designed and implemented. Auto IEED is an exit guide links to the building fire alarm system. When the alarm goes off, the greens and light LED on the evacuation door will light up, indicating which direction of floor you need to move to. For example, imagine that you are the occupants at 7th floor and there is a fire occur at 5th floor in the building. The lower part of the LED appears to be red and the upper part appears to be green. It means that you need to go to the floor above you and there is danger below. The same situation goes to the occupants at the floor who are supposed to go to the floor below him. Meanwhile, you and the other occupants will receive warning notifications about the fire conditions. Let's have a look on the project demonstration video. I'm Luigi and I'm going to demo my project Auto IEED. For your concern, this project is supposed to be installed and demo in the faculty. However, due to the pandemic of COVID-19 and MCO 3.0, I have to demo it at my house. By doing so, let's take some imaginary assumption. If the will represents a floor in the multi-storage building, and the common area connecting the door will be the staircase. Now, let's set up a small fire in the second floor and I'm the occupant in the first floor. The upper part of the LED strip is red and the lower part is green. It means that I need to go to the floor below me and there is danger above. The entire LED strip at the second floor are red since there is a fire inside. At the same time, I receive a push notification stating that there is a fire on second floor and evacuation is needed. Next, let's set up this small fire in the first floor and I'm the occupant in the second floor. The upper part of the LED strip is green and the lower part is red. It means that I need to go to the floor above me and there is danger below. The entire LED strip at the first floor are red since there is a fire inside. At the same time, I received a push notification stating that there is a fire on the first floor and evacuation is needed. Next, I will move on to part 2, technical presentations. The objective of these projects are to design and develop an emergency exit door indicator to make comparison between the conventional emergency exit system and the proposed emergency exit door system. Auto IED system is designed to detect the flame and smoke and to initiate the visual and audible signal that alerts and guide the building occupants in a fire evacuations. Therefore, it is helpless against fire controlling. During the project operations, I assume that the amount of smoke produced is sufficient to activate the system. Also, I assume that there is no smoking or children playing with matches around the sensor because it may lead to a false warning of fire. The component of the system have a probability of failing at any time, therefore is required to check, maintain and replace the component and battery at a regular interval for precautionary measure. The power supply to the system must be constant at 5 volt DC. And moreover, this system is intended to be installed at the exit of an exit route of a multi-story building because smoke detectors are subjected to false interpretations of fire when located near a dusty or steamy environment such as kitchen. Auto IED system consists of 4 major elements: the power supply unit, control and processing unit, alerting and indicating units, and detector. The detector system was constructed by the integration of DHT11 temperature and humidity sensor, MQ2 smoke sensor, KY026 frame sensor with not MCU ESP32. Meanwhile, the alerting and indicating units were constructed by the integration of piezo buzzer and SK6812 LED with not MCU ESP32. The not MCU ESP32 is responsible to read data from sensor and to trigger the piezo buzzer and LED strip. The data collected from the sensor will be uploaded to ThinkSpeed via internet, and the data collected will be stored and monitored on the cloud in real time. Suppose that there is a fire caused in the building and the data collected exceeds the threshold set. In that case, push notifications will be sent to the registered mobile device of the occupant using pushover applications. At the same time, the occupants can track the LED indications on the exit door to escape the building. The rescue team can also utilize the red indication of the LED to locate the site of the fire. The implementation of the auto IED system requires a constant and consistent 5-volt input voltage to supply the alerting and indicating unit and detector system. Therefore, the 7.4 volts to 5 volt voltage regulator was constructed, tested and verified using multi-sim. It can generate identical amount of the currents as applied at the input end. This circuit uniqueness is mandatory for the LED, which require a large amount of currents for operations. And the voltage drop of 2.4 volt is dissipated as heat, so a heat sink was used to protect the LM7X005 IC from being burned. This is the complete circuit connection of auto IED system. It is an integration of the 5-volt voltage regulator, power supply unit, control and processing units, alerting and indicating unit, and the detector system. So in practice, this project is designed to be implemented at the exit of an exit route. Hence, the auto IED system is intended to be mounted on both sides of an emergency exit door on each level. A total number of 2 layers were used in this project, so there will be total of 4 sets of auto IED system. I assume that the section facing the staircase is the outer side and the section facing the interior of the building is the inner side. There are 2 different sets of algorithms used in this project. One's for the inner side, another one is for the outer side. The algorithm at the outer side is written based on the fire condition on both layers, which is not 0 and not 1. The not MCU ESP32 is subscribed to the ThinkSpeed channel of another layer, and it will continually monitor the reading published to that channel and toggle the upper part and lower part of the LED. So 4 channels were created to store data from 4 sets of the system. And in ThinkSpeed, React was used to set the threshold, and ThinkHTTP was used to configure the content of the push notification in pushover. The system is keep connecting to Wi-Fi to obtain a massive range of data. The data are updated and represented in graphical forms on the ThinkSpeed, and the graphs are monitored in real time to understand the change in the surrounding temperature, humidity, and smoke concentrations over time. Meanwhile, when the data exceeds the threshold set in the React, the HTTP is triggered and a push notification is sent to the authorized mobile device via pushover. Based on the bar charts, our design auto IED system has lower power consumption or electricity usage than the incandescent and fluorescent type of conventional exit sign in all 3 domestic, commercial, and industry sector. Despite of the fact that its power consumption is higher than the LED type of conventional exit sign, but it is more powerful and useful in the evacuations. So this project has some significance. Firstly, application and commercialization potential. Emergency exit doors are required in all public buildings where there are many people, such as in KL. So it's required when a large number of people would need to escape from the building due to an unexpected fire event or disaster. The feature of this project is that its ability to detect the danger behind an emergency exit door. Therefore, the life of the occupant would not be at risk during an evacuation. Secondly, the sustainability. The world population has risen to over 6.3 billion people, and as population growth is an underlying factor for the demand of multi-storage building due to the limitation of land property, this project is necessary to install in the multi-storage building to warn the people that there may be a fire and evacuation may be needed. Thirdly, environmental friendly. This project works by flashing the red and green LED as indicator. LED require much less electricity than most of the other form of the emergency exit illumination, such as incandescent and fluorescent, as shown in this bar chart. So, and moreover, LED are more cost effective and have a long shelf life of over 10 years. So I would like to conclude by emphasizing the fact that smoke and fumes are produced when a building and its contents start to combust. Auto IED can help you to escape quickly, safely by flashing the LED, which indicate the right directions on the emergency exit door. Thank you.
Thanks. So I would like to invite Q&A from judges.
Yeah, Chingy, your design seems to requires high maintenance, right? You have so many sensors, the smoke sensor, flame sensor, temperature and humidity sensors. So how would you overcome this if, let's say, that you want to commercialize this? The maintenance is going to be, may not be that practical. What's your comment on this?
Before we put up the system, we will first test all the sensor, and then we will set a time interval and check the sensor regularly.
And compared to conventional, the emergency exit signage, how much costlier is your setup?
My setup for 4 system, which is for the 2 level, is around 250. Means that one system is around 60 ringgit.
But per exit door, you need to spend 250, right?
Yes.
And the conventional, the normal, those green color exit sign, how much is that? Maybe
That one is around
5 times more.
That one is around 80 to 90 ringgit.
Okay, all right. So yours is definitely more expensive, so it could be quite prohibitive in real life, application.
Yeah.
All right, thank you.
Hi, Chingy. This is Maya here. So I see you put up your use case quite clearly, and I see this is a quite useful solution since this is related to risk hazard, and so I think probably like what Ming mentioned, probably only the cost will be a limitation. So my question is regarding on your assumption, right? You said you listed one of the assumption, right? For your solution to work, you assume there's need to be sufficient amount of smoke. So how you actually quantify that? So I'm concerned, how much smoke will actually make your solution to work or get started? Do you have a way to quantify this?
Actually, I set my threshold according to a journal article. It's called it's like this. It's called the Brain Fox project, and in the project it stated that because in smoke, carbon monoxide is the main component. So according to the OSHA, Occupational Safety and Health, they quantifies the IDLH, which is the intermediate dangerous level for life and health of the carbon monoxide is 1,200 ppm. So to have more, for the occupant to have more time to evacuate, I set my threshold to be 800 ppm.
Okay, I see. All right. Thank you, Chingy.
Thank you.
Any other questions?
Hi, Chingy. Hi. Hello.
Hi.
Hi, I'm Huyen. Yes. Good project. The video demonstration never failed to disappoint me. I continue to be impressed every time I see the video. So good job. my
Thank you.
question, my question to you that you mentioned 3 parameters that is used to trigger the alarm.
Yes.
The smoke, temperature, and then the presence of fire. So what is the logic that you implement and what's the criteria? Suppose if only one parameter is triggered, but the other 2 is not triggered, will it still trigger the alarm?
No, I use the AND operator so that when a fire is present and the smoke is over 800 particle per million and the temperature is over 30x, then only the alarms will be triggered.
Okay, so all right, thank you.
Right. Thanks, comment from judges. So may I invite judges to comment on the overall projects?
Yeah, I definitely agree that the current emergency exit design, is overdue for a total, revamp or to be improved further, right? So you come up with a solution that is both, innovative and very useful, and it will give whoever that stay in the apartment a peace of mind of where to evacuate during emergency. I think that is great. If you can make your so-called design more compact, your those LED stripes could be, maybe subjected to abuse. People may take it out or something, so the maintenance cost will increase. So try to make it more compact, and I'm sure you also need to test it out into in different environment, different condition before you can convince whoever that is going to implement this to to use this, right? So all in all, is a very good project, and I hope that you will have many successes to commercialize this, right? All right, thank you.
Thank you.
Thanks, comments from the judges and also Qingyi teams for the nice works and also presentations. So we have come to an end of all the presentations. As mentioned by Dato' Shida just now, no matter what is the outcomes of today's competitions, you all already appears as the winners of being shortlisted for the top 5 finalists. So before we end these sessions, I would like to check with Keysight. Is there any follow-ups action from your side, or is there any comments to the participants?
Yeah, we have a very great session, although it's just 2 hours, but this is a 1 year work, compressed into just 2 hours. I believe we have also lecturers on the line, supervisors. You all have done a great job in nurturing all these futures, who they are going to come out to work pretty soon, right? So you are getting them ready with all these practical, knowledge, and I'm sure that they'll do well in wherever they go, right? So thank you for all the effort that the university have put in, and we are glad that as a Keysight we are able to be part of, your success, right? Thank you.
Thanks, Mingwei, for the speech. So at the end, all judges are advised to log in to the separate online sessions given for internal discussions, if any interested projects. So the winners will be announced via Innovate's Malaysia websites. So at the chairs of today, I would like to thanks for all the audience for attending these meetings, and also efforts from the judges in commenting and improving the project as well. And also thanks to the participants for putting up a lot of efforts in making this project a success. So with that, thank you so much. And during this COVID-19, take care and stay safe. Have a nice day, everyone. Goodbye.
Okay, thank you,
Thank you.
Dr. Chi,
Bye.
and everyone.
Thank
Bye.
you.
Okay,
Thank
bye
you.
bye.
Bye,
Thank you
everybody.
very much.
Thank you.
Thank you very much, Keysight.
Thank you. Goodbye.
Thanks.
Thank you.
Bye bye.
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 Bye.